No piece of equipment runs forever. We inspect the boiler in our plants at least once a year to look for problems that might cause shutdowns or reduce the boiler's efficiency. There are two major areas that are inspected, the fire side and the water side. The fire side is the surfaces inside the boiler that are exposed to fire and hot gases. The water side is the inside surface of any boiler component that contains water or steam. Now, what we're going to be talking about here is how to detect potential problems during a routine fireside inspection. That means we'll be inspecting the surfaces inside the boiler that are exposed to fire and hot gases. Even though you're not the official boiler inspector, the work you do allows you to detect certain problems that can affect boiler reliability and efficiency, if you know what to look for. So, what we'll do now is to go through a typical fireside inspection and point out some of the things that you'll need to know. Several preparations must be made before inspecting a fireside. Before you begin, check with your boiler operator to make sure that bottom ash has been pulled and all soot blowers have been blown. Then, check to see that combustion deposits like ash and slag have been cleared from the boiler. You won't be able to get all of them, but the inside of the boiler should be as clean as possible. The boiler should be shut down and tagged out. Tagging out guarantees that none of the valves will be tampered with during inspection. Once the valves are tagged out, access and inspection doors should be opened to cool down the boiler. Immediately after shutdown, and while the boiler is still hot, go to every opening in the boiler and listen for leaks. If there's evidence of leaks, note the location. After you've listened for leaks, the boiler should be cooled down. Now, once these preparations are complete, the first fireside component you'll be looking at is the water walls. The water walls are made up of water-filled tubes that line the inside of the furnace. When the furnace is in operation, heat is transmitted through the tubes to the water, which is eventually converted to steam. Water walls have four common problems: overheating, support failure, ash accumulation, and refractory failure. Overheating in the water wall tubes leads to warping, leaks, and tube blisters. Warping is caused when a section of the water wall overheats. This is fairly easy to spot. It may be indicated by a large number of leaks in a small area of the water wall. Now, tube blisters, like these right here, are bulges in the tube surface, which form when the tube metal becomes so hot that it softens and is pushed out by the boiler pressure. Now, the next problem, support failure, shows up in the water walls as vertical misalignment of its tubes. Water walls are attached to headers that are usually hung from the top of the boiler. Now, if the supports holding up a section of the wall break, that section will sag. And if that happens, you'll see a section of tubes that is lower than the others. It's important to check this out because support failure could lead to the collapse of the entire boiler. Now, the third problem affecting water walls is excessive ash accumulation. This can be plainly seen by looking at the water walls. There are two kinds of ash accumulation to look for: ash that adheres to the entire water wall and clinkers that are fused to it. Now, clinkers are dangerous since they're large and they can hurt someone if they fall. Be sure to clean them away before working inside the boiler. Now, another problem we need to discuss is refractory failure. This is a piece of refractory right here. It acts as insulation in the boiler. Refractory failure usually occurs wherever refractory is exposed on the inside of the water wall. Typical areas where you can see refractory are the burner openings, the ash hopper area, inspection doors, and air inlets. And what you should look for are things like general deterioration, or cracks, or water damage. Refractory has other potential problems: spalling, cracking, and slag attack. Spalling is the flaking away of refractory. It's caused by improper installation of refractory, by sudden temperature changes, or both. Cracking is due to improper installation or sudden temperature changes. Slag attack is the chemical reaction of ash and refractory. Slag attack erodes refractory, reducing its thickness. It melts the refractory and causes it to run off. Slag attack may also cause refractory to become soft and crumbly. In some cases, slag attack will produce a glassy surface. Refractory failure, overheating, support failure, and excessive ash accumulation are not the only things to look for during a Fireside boiler inspection. There are also metal problems, such as surface deterioration, failure of previously repaired areas, failure of construction welds, and leaks. Surface deterioration, like water wall erosion, can be caused by steam or water, fuel, combustion gases, or soot-blowing air or steam. Erosion can cause tube thinning. Tube thinning is a serious concern because the thickness of tube metal provides strength to contain boiler pressure. Now, these tube sections were cut out of a water wall. You can see how much thinner this side is than this side. When the thickness of a tube is reduced, the tube is weakened, and this can result in tube failure. All boiler tubes have an acceptable minimum wall thickness. When you inspect the tubes, you have to be aware of the amount of tube thinning that can be tolerated before repairs are necessary. Now, to some extent, tube thinning can be determined by looking at and feeling the tubes. You can tell that local thinning caused by erosion has occurred because you can see and feel a gouge in the affected tubes. Erosion can happen wherever there is any flow across a boiler component. Erosion from steam or water is caused by leaks in the water wall tubes. When a tube leaks, a stream of water or steam shoots out, and if it hits a nearby tube, this stream of water or steam will wear away some metal, possibly causing more leaks. Carefully inspect the area around leaks for evidence of tube erosion. Eroded areas, as well as the original leak, should be repaired to guard against future tube failure. Other problems besides erosion may crop up in the soot blowers. Soot blowers enter the water walls through openings that should be checked when inspecting the water wall. Look for damage to exposed refractory in and around the openings. Make sure the openings are clear of ash and slag. Also, check to make certain that all the soot blowers fully withdraw. Heat in the furnace can damage the soot blower lance. Erosion is still a major concern here. Check the tubes around the soot blower openings for erosion that may be caused by steam or air coming from the soot blowers. If you find any, the soot blower may be improperly aligned, that is, blowing against rather than across the tubes. Now, if that has happened, both the soot blower alignment and the erosion must be corrected. Corrosion is similar to erosion. Corrosion is the gradual wearing away of metal by chemical action. Rust is an example of corrosion and is most likely to occur when tube metal gets wet. Another example is corrosion from soot or ash. Soot or ash can be found anywhere in the boiler. Generally, though, corrosion occurs in out-of-the-way places. Corrosion caused by rust, soot, or ash is detectable because of its coloration, mostly red or green or yellow. Corrosion and erosion are only two problems that you might find on the outside of the water wall tubes. Other problems to watch for are pitting, cracking, and scale formation. Pitting is a type of corrosion and appears as small craters in the surface of the tube metal. In severe cases, pitting can weaken the tubes, eventually causing failure. Cracking can also result in tube failure. Any sized crack in the tube surface weakens the tube. Once a crack is formed, it tends to grow deeper. Over a period of time, the crack will penetrate the tube wall and cause a leak. Finally, scale on the outside of the tubes presents two problems. For one, scale like ash insulates the tube and prevents proper heat transfer. This reduces boiler efficiency. The second problem is that corrosion may occur beneath the scale where it can't be seen. Checking for all these problems does not end your inspection of the water wall. Old repairs must also be checked. Careful records should be kept of each repair, what it was and where it was located. During each inspection, previously repaired areas should be examined to make sure the repairs have not failed. A failure that happened in a particular area once may happen there again. Another water wall item to check out is construction welds. These joined the tubes together when the boiler was first built, and they're subject to leaks. Leaks in general are the fourth potential problem in the water wall tube metal. Since the boiler is shut down during inspection, water may not be spouting out of the leaks unless the boiler is under pressure. So, to detect leaks at the welds, look for dampness on the tubes or discolorations of the water wall. Any visible erosion or corrosion anywhere may be evidence of leaks. Also, any tube crack may be a leak. We've gone over 4 potential problems with the metal in the water wall tubes. Surface deterioration, including erosion, corrosion, pitting, cracking, and scale formation. Failure of previously repaired areas. Failure of construction welds. And leaks. Earlier, we covered preparations for a fireside inspection and many of the problems you must look for in the water walls. Let's pause for a few minutes so you can review all of this material before we continue. Now that you're familiar with some of the problems to look for during water wall inspection, let's discuss how you find them. We'll go over some inspection procedures and why they're needed. Boiler inspection actually starts before you enter the boiler. Listening for leaks, for example, is part of that pre-entry inspection. Most of the inspection, though, takes place after the boiler has cooled down and you can get inside. Once inside the boiler, you can determine the exact location of leaks identified during your pre-entry inspection. You might be wondering how you can get close enough to the boiler components to inspect them. After all, a good-sized boiler may have water wall 150 feet tall, and it's difficult to see the kind of details we've been discussing if you're looking up at them from the bottom. Well, there are 2 ways of coping with this distance: movable and fixed scaffolding. A movable scaffold, like a spider, can be used for looking over most of the water wall. Fixed scaffolding can be erected inside the furnace to reach areas that need to be inspected. You probably won't use fixed scaffolding unless extensive work must be done on the water wall. Scaffolding can be hung from the furnace roof or built up from the bottom of the furnace. Fixed scaffolding provides a stable work platform, but it takes a long time to build. You can also inspect the water walls from the bottom of the furnace and through the inspection doors. It's easy and quick, but it's not very thorough. Using a spider is more thorough, while fixed scaffolding gives access to a larger area. Whatever method is used, the best possible lighting should be rigged in the boiler in order to improve your visibility. When you begin the inspection process, there are several tools that you should have with you: an inspection mirror, a small hammer, a scribe tool or knife, a wire brush, and a flashlight. An inspection mirror will be useful when you look at the water wall through the inspection doors. Use it when inspecting places in the water wall that are not easily accessible. Now, a scribe tool or knife is used to scrape away ash buildup and scale to expose the bare metal. A wire brush can also scrape away ash and scale. A flashlight is needed because the boiler's normal lighting may not be adequate. One inspection procedure that may require a special tool is detecting tube thinning. Now, sometimes tube thinning can be determined simply by looking at or touching the tubes. You might feel a gouge or depression. Some thinning, though, is harder to detect and can only be determined by an ultrasonic measuring device. Now, an ultrasonic measuring device uses a high-frequency sound beam to measure the actual thickness of the tube. The measurement can then be compared to the minimum allowable wall thickness to determine if repairs are necessary. Accurate ultrasonic measurement requires a clean metal surface. Preparation often includes sandblasting the metal surface to ensure accuracy. Ultrasonic measuring is one kind of non-destructive testing, or NDT. It's an excellent method for tube measurement, but it's not the only one. A sample cut from a tube is another way to measure thinning, but that's destructive. So the preferred method is to use ultrasonic measuring. While tools like the ultrasonic measuring device are helpful, the most important ones are your eyes, ears, hands. Look for problems. Listen for running water that indicates leaks. Feel a tube's surface to determine its condition. Sometimes you'll feel things that your eyes have missed. Remember that safety is important during all phases of fireside inspection. Different inspection methods inside the boiler require different safety measures, yet there are standard safety procedures you should always follow no matter what you're doing. Make sure there's adequate ventilation in the boiler. One way of doing this is to set up a fan in the inspection door like this. Also, make sure that no harmful gases are present. Clinkers and accumulations of ash should be removed from the boiler walls. You don't want them to fall on you while you're inside the furnace. Besides standard safety gear like a hard hat and safety shoes, additional equipment including eye protection, gloves, protective outer clothing, and ear protection might also be necessary. Special precautions are needed when you're above the boiler floor. For example, using a spider calls for additional safety precautions because you're working at great heights. Before the spider is installed in the furnace, check its cables and hoses. Make sure they're in top condition. When you're ready to go up, have all your tools with you. These should be tied to you or to the spider. You don't want them falling on someone below. Wear a safety harness with safety lines attached. Also, check how much weight the spider can carry to ensure against overloading. Watch for chafing of the spider cable, and don't forget to read through your plant safety manual and comply with all of its requirements. Fixed scaffolding also requires special safety precautions. If you use scaffolding, make sure it complies with your plant safety manual. Again, don't overload it, and secure all tools. Whether you're using a spider or scaffolding, if you find an unusual condition or a failure, you should photograph it. Photographs make your description of the problem easier to understand, and they serve as a permanent visual record of what went wrong. Well, we've now covered general tube thickness and soot blower problems, visual inspection techniques, and ones that use measuring devices, and the importance of safety precautions. So take a few minutes now to clear up any problems or questions you might have. There are still 4 other water wall problems we need to talk about: clinker damage, flame or fuel impingement, trouble with burner openings, and trouble with inspection doors. Now, clinker damage occurs when clinkers high in the furnace fall and hit the water wall tubes at the bottom of the furnace. This causes tube bending, crimping, and denting, and it also wears away the tube metal. Severe bending is a serious problem because it'll restrict water flow, which leads to tube overheating and failure. Wearing away of the tube can result in tube failure as well. Be sure to check for all these conditions when you inspect the clinker impact area at the bottom of the boiler. Flame and fuel impingement occur near the burners. Impingement is the throwing of flame and fuel against the water wall rather than into the center of the furnace. Flame impingement can be detected by discoloration or blistering of boiler tubes in the burner area. Fuel impingement is found in the same general area as flame impingement and causes tube erosion. Look for this erosion as well as fuel accumulation to detect fuel impingement. Another case of fuel impingement is faulty burners that throw unburned fuel across the furnace. If you find fuel impingement, you're likely to find flame impingement as well, so be on the lookout for both. If you find fuel or flame impingement, the burners must be examined carefully. Burner parts must be checked for wear due to erosion, damage from heat, and improper alignment. If there's evidence of flame or fuel impingement on the water wall, check your boiler's manufacturer's manual for alignment instructions. Refractory at the burner opening should also get close attention. This refractory is exposed to particularly high temperatures. While checking this refractory, look to see if ash and slag have accumulated on the refractory or in the burner opening. Now, they could prevent proper burner operation by obstructing the burner openings where fuel enters the boiler. Burner openings in the water wall contain air ports that supply combustion air to the furnace. Sometimes air ports are built directly into the burner. These should be inspected to make sure they are clear and are allowing a free flow of gas. Also, make sure they're not deformed. Deformed air ports alter the correct pattern of air flow. When looking at inspection doors from inside the boiler, watch for two things: blockage from ash or slag accumulation and deterioration of the refractory in the inspection door openings. While checking the water wall, inspect the radiant superheater if your boiler has one. A radiant superheater is built into the furnace wall just above the water wall. Since the radiant superheater is located in the same area as the water wall, you should inspect both at the same time. Radiant superheaters can have the same problem as any other boiler component. These include overheating, support failure, excessive ash accumulation, and failure of refractory around the superheater. Typically, this refractory will not be inside the superheater, but found in the walls near the superheater. Also, look for metal problems: erosion, corrosion, pitting, cracking, or scale on the tube surfaces, failure of construction welds, and leakage. Finally, since radiant superheaters are made of tubes, you must also check for tube thinning, soot blower problems, and deterioration in those areas where tubes enter and exit the boiler. Radiant superheaters can have many of the same problems as the water wall because both are located in the same general area. These same kinds of problems occur throughout the entire boiler, but most components also have some individual features that require inspection. As I've said, many of the problems that affect the water walls can occur throughout the boiler. With that in mind, and remembering that your inspection actually begins while the boiler is still pressurized, let's talk about problems and problem areas in the superheaters and reheaters. There are many names for superheaters based on the way they absorb heat, their location in the boiler, and their tube arrangement. Superheater names will vary from plant to plant, but we'll cover some typical ones. We've already talked about one type, the radiant superheater. Now we'll discuss some others: the platen, pendant, and horizontal superheaters. We'll take them as a group because their construction and kinds of problems are very similar. We'll include reheaters here for the same reason. Remember, superheaters and reheaters are different components, but they are built in much the same way and suffer from similar problems. So the material we'll cover applies to both. General problems that show up in superheaters and reheaters include overheating, support failure, excessive ash accumulation, and refractory failure around the superheaters. Overheating in superheaters and reheaters can be detected by warping, leaks, and tube blisters. Warping is immediately apparent when you examine the component. Superheater and reheater tubes are supposed to be in line and parallel to each other. If warping has taken place, the tubes will literally stick out like a sore thumb. Warping may also cause an additional problem. Warping alters the distance between tubes, which in turn changes the flow pattern of the gases passing through the superheater. The flow can then become channeled in such a way that erosion increases on some tubes while ash builds up and collects in other places. Check for these when you find warping. And while you're in the area, be on the alert for leaks. If you find a leak in the superheater or reheater tubes, the area around them should be inspected for blisters. Blisters are an indication of overheating. Blisters can be pretty hard to find, especially if they occur on a tube inside the superheater bundle. One way to check these hard-to-find blisters is to shine a light along the length of each tube. And if a tube is blistered, the blister will cast a shadow. It is important that you recognize warping, leaks, and tube blisters as symptoms of overheating. Understanding the primary cause of these problems will make a difference in the way you deal with each one. For example, there might be operational adjustments that can be made to correct overheating. Another general problem in superheaters is support failure. Watch for support failure when inspecting the superheaters. Total support failure is a very serious problem because it can lead to collapse of the superheaters. Pendant and platen superheaters are suspended from the top of the boiler. Each tube element is attached to headers located outside the hot gas path. The headers have their own supports. If the header supports break, you may not be able to see the break itself, but you will notice that the superheater tubes are out of position. Another thing to look for during superheater inspection is clip and tie bar failure. Clips and tie bars hold the superheater elements in proper position in the hot gas path. Failure of clips and tie bars makes it easier for tube elements to warp out of position. Some supports for the horizontal superheaters are located within the hot gas path. Usually this kind of superheater is supported from above. However, there may be tie bars to hold the superheater's bundles together. Tie bars also provide support for the lower parts of the tube elements. Since these supports are exposed to hot gases, they're more likely to fail than supports located outside the hot gas path. Regardless of the type of supports a superheater uses, all superheaters and reheaters, like all boiler components exposed to ash, are subject to excessive ash accumulations. Now, some of this ash accumulation is unavoidable. But the important points to remember here are that it is important to detect ash accumulation and that areas near the accumulation should be closely examined. The final problem common to most boiler components is refractory failure. Refractory in the superheater and reheater areas is no different from refractory elsewhere in the boiler. You should look for the same kinds of refractory failures in the superheaters and reheaters that you look for in the rest of the boiler, especially spalling and cracking. Well, we've now discussed 4 more water wall problems: clinker damage, flame and fuel impingement, trouble with burner openings, and trouble with inspection doors. We've also covered some things to look for in the superheaters and reheaters, including overheating, support failure, excessive ash accumulation, and refractory failure. Let's take a few minutes to go over the material in your texts and clear up any questions or problems you might have. There's another group of problems in the superheaters and reheaters that's common to all metal boiler components. This group includes erosion, corrosion, cracking, problems in areas of prior repairs, problems with construction welds, and leakage. Accelerated erosion is caused by warping and ash blockage. Erosion is therefore most likely to appear where gas flow is particularly rapid or where ash concentration in the gas flow is particularly heavy. Ash concentration may be heavy where gas flow makes a turn. Tubes at the outside of the turn are especially vulnerable to ash erosion because there the gas flows faster and loose particles tend to become more dense and abrasive. Erosion in the superheaters and reheaters can also be caused by a steam jet from a leaking tube. A steam jet from a leaking tube can erode the metal of adjacent tubes until they also leak. When inspecting superheaters and reheaters, be sure to look for evidence of erosion in areas around known leaks. Also, eroded areas may indicate leaks that were not previously detected. The next metal problem is corrosion, a chemical attack of the tube metal. Corrosion can be caused by the metal's exposure to air and water, resulting in rust, exposure to acid formed by sulfur in the fuel combining with water, and exposure to corrosive scale. Corrosion can be indicated by discoloration or pitting of the tube metal. Tubes with scale on their outside surfaces should be scraped in several places to determine if corrosion is taking place beneath the scale. Corrosive scale is most common in oil-fired boilers, so be alert for corrosive scale when inspecting oil-fired boilers. Regardless of the fuel used to fire a boiler, all tube surfaces must be inspected for erosion and corrosion. Something else to look for on the tube surface is cracking. Superheater and reheater tubes are more susceptible to surface cracks than water wall tubes. This is because superheater and reheater tubes operate with higher metal temperatures than water wall tubes. Another area of concern are places in metal components that have been previously repaired. Prior repairs must be inspected closely. To inspect them, you need to review the records of what work was already done. These records also indicate which areas of the superheaters have had past problems, and that should give you some idea of where you might expect future trouble. Construction welds present other areas for potential failures. It's particularly important to inspect welds in the superheaters and reheaters because they may connect two different metals. Superheaters and reheaters are often made of several different metal types. Bimetallic welds join two kinds of metal and are especially prone to failures. Attachment welds may also be found in the superheater. These welds hold support clips on the tubes. Tube failures are common in the areas around these welds. The final problem concerning metal components is leakage. And remember, right now, we're talking about inspection with the boiler depressurized, so you might not see the leakage. However, any evidence of leakage should be noted, the source of the leak determined. This may require some very careful investigation. But one way to detect leaks when the boiler is shut down is to use compressed air to pressurize the superheater. This makes it possible to hear air escaping from any leaks. Well, now that we've talked about problems with metal components, we'll discuss two more problems that occur in tube-type components: tube thinning and soot blower problems, both of which also showed up in the water walls. Tube thinning affects the tube's strength and ability to contain pressure. It can sometimes be detected by direct observation, but for a more precise measurement of tube thinning, an ultrasonic instrument must be used. Now, with this, you measure tube thickness on a worst-case basis. For example, if one section of the tube exhibits severe ash erosion, you would take measurements in that area. Wherever a tube has a bend in it, you have a possible area for erosion. Erosion takes place on the inside of the tube, but it is usually detected from the outside. Measurement from the outside of the bend should indicate whether tube thinning from erosion is occurring on the inside of the tube. Soot blowers are the source of other problems in tube-type components. If your boiler uses retractable soot blowers, the soot blower openings should be inspected. Look at the refractory conditions, making sure the openings are free of ash, and slag. If the soot blowers are retractable, they should move all of the way out of the boiler. Permanently installed soot blowers, on the other hand, have different problems. Check permanently installed soot blowers for warping or other damage from heat, improper alignment, erosion, blockage or wear of the blowing nozzles, and improper attachment. In the soot blowing areas of both kinds of soot blowers, you should inspect boiler tubes for erosion caused by the soot blower. Inspecting the superheater to find these problems is usually easier than inspecting the water walls. Access to the superheaters is generally accomplished by crawling through doors at either end of the tube bundles. Usually only a minimum amount of scaffolding is required for access. Now that doesn't mean that the superheaters don't pose problems. Platen superheaters are hung above the furnace and can only be reached by scaffolding or spiders. Other kinds of superheaters present a unique access problem because of their construction. Their tubes are packed so tightly together that the outside tubes in a bundle prevent close examination of the inside tubes. When it's necessary to work on the inside tubes, access to them is gained by spreading the outside tubes apart. They are then held out of position until the work is completed. Now, this tube spreading method is effective, but it is time-consuming and not practical for periodic inspection. An adequate inspection can be done by looking down the aisles in the superheater bundle, and this long-handled inspection mirror will allow you to look inside the bundles more closely. Spreading the tubes solely for inspection purposes should only be done as a last resort. Other than tube spreading, superheater and reheater inspection uses the same techniques and tools as water wall inspection. Well, our discussion of superheaters and reheater inspection is centered on several groups of problems. One group of problems was common to almost every boiler component: overheating, support failure, excessive ash accumulation, and refractory failure. Another group of problems concerned metal components: erosion, corrosion, cracking of the tube surface, problems with areas previously repaired, problems with construction welds, and evidence of leakage. The two other types of problems we went over affected tube-type components. These were tube thinning and problems with soot blowers. Finally, we touched on a special problem: access to the inner tubes that might be encountered when performing superheater and reheater inspection. Each individual problem has its own cause and detection devices. It's important that you know all of them. During inspection, you're likely to see most of the conditions we've examined. So why don't you take some time now to review all of this material in your text and solve any questions or problems you might be having. So far, we've inspected the water walls and the superheaters and the reheaters. Well, it's time now to inspect two more boiler components: the economizer and the bottom ash hopper. Economizers are affected by general boiler problems: overheating, support failure, excessive ash accumulation, and refractory failure. Since the economizer is a tube-type component, it's also subject to tube thinning and soot blower problems. Excessive ash accumulation is a particular problem in the economizer. Most economizer tubes have fins or gill rings that can become blocked with ash more easily than bare tubes. There's another problem. Economizers are subject to accumulations of unburned fuel. Now, this is a fire hazard and is potentially explosive. When checking for ash blockage in the economizer, be sure to see if the ash includes unburned fuel. The economizer should also be checked for erosion, corrosion, general surface deterioration, problems with old repairs, problems with construction welds, and evidence of leakage. Economizer tubes are especially prone to corrosion because The economizer area has the lowest temperatures of the components we've discussed, so condensation is more likely to form in the economizer. Condensation leads to corrosion, especially if the boiler fuel has sulfur in it. Corrosion often shows up in the row of tubes where the hot gases leave the economizer. Comparing the outlet row of tubes with that of the inlet row of tubes should give you some idea of how much corrosion has taken place throughout the economizer. To inspect the economizer, techniques are used that are similar to those for inspecting the superheater. Like the superheater, economizers have tubes packed so close together that it's difficult to see the tubes within the bundle. Inspection of the inside tubes is generally made by looking down the lanes between the tubes. And here too, closer inspection can be accomplished by using a long-handled inspection mirror. As a last resort, the tubes may be spread apart to provide access to the inside of the bundle. It's important to look at the inlet and the outlet row of tubes because they're accessible, and their condition will give you an idea about the condition of the inside tubes. Another component that requires inspection is the bottom ash hopper. Now, the bottom ash hopper must be examined for 5 problems that affect the refractory inside the ash hopper. These are the effects of rapid temperature change, ash buildup, erosion, surface deterioration, and problems in previously repaired areas. The bottom ash hopper can have refractory problems caused by the bottom ash that collects there. The ash is very hot when it enters the hopper. Normally it is cooled quickly by water in the hopper. However, this water must be drained every once in a while to get rid of the accumulated ash. While the hopper is empty, hot ash can heat the refractory on the inside of the hopper. This problem is made worse by the sudden temperature change that occurs when the ash hopper is refilled with water. The combination of heating and then sudden cooling of the ash hopper can lead to spalling and cracking of the refractory. Ash buildup is another problem in the bottom ash hopper. All bottom ash should be removed from the hopper when it is drained. Some ash may remain in the hopper if the spray nozzles are misaligned. If some ash does remain in the hopper, note it during inspection. The remaining ash will have to be removed manually. Early detection and correction of a problem within the ash hopper will avoid repeated manual ash removal. Another problem that can show up in the ash hopper is erosion of the refractory. Anytime water flows over refractory, there's the possibility of erosion. Be sure to check the general surface condition of all of the refractory inside the ash hopper. Things to look for include spalling, cracking, and erosion. Also, if you can see refractory anchoring devices at the refractory surface, the refractory is either badly worn away or was improperly installed. Previously repaired areas must also be checked when inspecting the ash hopper. Refractory breakdown in the bottom ash hopper is a fairly common occurrence. An ash hopper's refractory may be repaired many times, so inspect the refractory to make sure it's holding up. 4 more areas in the ash hopper are concerns during an inspection: the boiler bottom seal, the ash spray pipes and nozzles, the ash gate, and the ash hopper inspection doors. There are only general areas in the ash hopper, the ones that I've mentioned here, so some boilers will have even more places that require inspection. The boiler bottom seal is a seal between the boiler and the ash hopper. The boiler bottom seal isolates the furnace from its surroundings. 2 typical seal types are the corrugated seal and the sliding seal. The corrugated seal type allows the boiler wall to expand. The corrugated seal is accordion-like, an accordion made of corrosion-resistant steel. The sliding seal type is an overlapping metal joint which allows the boiler wall to expand. This type of seal uses water to prevent any flow of gas into or out of the boiler. Boiler bottom seals should be inspected for the 5 basic common problems we discussed earlier: overheating, ash buildup, erosion, general surface deterioration, and problems with old repairs. In addition, the metal parts of the seal may be corroded. Your inspection should verify that the seal between the ash hopper and the boiler is tight. Also, there must be nothing to prevent the expansion of the water wall. If you have any question regarding how your boiler's bottom seal works, consult your boiler manufacturer's instruction book. Most ash hoppers use pressurized water to stir up the bottom ash being removed from the boiler. This helps get all of the ash out of the boiler. Pipes and nozzles are used to direct the water spray. You must inspect these pipes and spray nozzles for ash blockage and misalignment caused by clinkers falling on them. The nozzles are aligned correctly if they direct their spray towards the ash gate, that is, where the ash leaves the boiler. And the nozzles should not spray directly at the refractory. That'll wear it away. The bottom ash hopper's ash gate should be inspected for proper operation by opening and closing it several times. The ash gate is underwater most of the time, so it has its own seals to prevent leakage. When you inspect the ash gates, these seals should be checked for any signs of leakage. These include corrosion, nicks, tears, burn spots, and torn gaskets. Like the ash gate, some of the ash hopper inspection doors are usually underwater. These must also be examined for leakage. All the inspection doors should be checked to verify that they're in good working order. Well, we've now discussed inspections of the boiler's economizer and ash hopper area. You've seen some of the potential problems. You should have a pretty good idea of what to look for when inspecting the inside of a boiler. When your inspection is finished, there's one final procedure you must never forget. Be absolutely sure that no one is left inside the boiler. Now, this may sound obvious, but it's truly a matter of life and death. Be positive that no one is left inside that boiler after inspection. Also, before putting the boiler back into normal operation, clear away scaffolding, tools, rags, anything else you may have brought inside. In short, after inside inspection, empty the boiler of everything: people, equipment, trash. Now, that's the last step for inspection inside the boiler. Still to come is the inspection of the outside of the boiler, which we'll discuss after you take some time to go over all of this material in your text. So far, we've been inspecting the inside of the boiler. However, the exterior of the boiler requires inspection too. Outside inspection means the boiler casing and dead air spaces where headers are located. Before you begin the inspection, talk to the operators. Find out if they know any of the problems with the boiler casing, problems like leaks, hot spots, or blistered paint. Operators can save you time and trouble, so don't hesitate to ask them questions about the boiler. The boiler casing, which is the outer steel skin of the boiler, is subject to those 5 common problems we keep seeing throughout the boiler: overheating, support failure, corrosion, problems in areas of prior repairs, and problems with construction welds. Some signs of overheating are burned or blistered paint. In fact, the casing may even get red hot. Overheating of the boiler casing leads to buckling. This is caused by expansion of the casing metal. You can detect buckling by bulges and cracks in the boiler casing. Casing buckling can cause problems inside the boiler, so look closely at the inside components in the area where buckling takes place. The casing is hung at the top, so many of its supports are located there. To determine if there is casing support failure, look for broken or loose hangers, loose attachment bolts or pins, broken attachment lugs, and failure of any of the steel columns or beams from which the boiler is hung. Corrosion of the boiler casing can be caused by moisture, and it's a problem that can show up anywhere. Indications of corrosion are discoloration, roughness, and holes in the casing metal. Unpainted steel is particularly susceptible to corrosion attack. A previously repaired area in the boiler casing may not only be the source of current problems, but also indicates a previous casing problem. It's a good idea to inspect any previously repaired areas to verify that the repair work is holding up and that there have been no reoccurrences. Always check the construction welds in the boiler casing. Casings are constructed from large steel plates that are welded together, and the welds should not be cracked or corroded. There are still 4 more areas we need to discuss in connection with inspection of the boiler casing and its external features. These are casing stiffeners, casing penetrations, the boiler drum, if there is one, and safety valves. Casing stiffeners are projections from the casing that have been installed to give the casing added strength. They look like big fins welded to the casing. These welds should be examined for cracks and corrosion. Casing stiffeners are also good indicators of buckling. If the casing buckles, the stiffeners will bend. Bent stiffeners may be easier to see than bulges in the casings. Casing penetrations are the places where pipes or tubes go through the boiler casing. These are weak areas of the boiler, and failures can start here. Also, thermal expansion may press the pipe running through the boiler casing against the casing itself. This can damage the casing and the pipe. A hole in the casing can lead to corrosion. While inspecting the boiler casing, you should also inspect the exposed parts of the boiler drum or moisture separator. When inspecting either one of these, look for signs of corrosion and cracking where the metal is exposed. Check the welds on all the pipes and tubes attached to them for cracking and evidence of leakage. Verify that the insulation is intact and that it has not been damaged by water. Take a look at the safety valves. They can be inspected when the casing inspection is done. A complete safety valve inspection requires the valve to be disassembled, but that's not the kind of inspection we're talking about. We'll talk about that inspection another time. Here, we want to check 2 things: that the hand releases are installed and that the valves are not gagged. The gag, placed here, is a device that keeps the safety valve from opening. When installed, it prevents the safety valve's function of relieving pressure. Well, that covers inspection of the boiler casing. Now, let's talk about inspecting dead air space. Dead air spaces are enclosed areas outside the hot gas passages where the headers are located. These headers are your primary concern when inspecting dead air spaces. There are several common problems associated with the headers. We'll cover 6 of them: support failure, evidence of leakage, corrosion, cracks, problems in areas previously repaired, and problems with construction welds. Pay particular attention to the header supports when you inspect the upper headers. These supports hold up part of the boiler, so check the headers to make sure they appear level and in proper position. When incorrect, these are both indications of support failure. Watch for broken or loose hangers, loose attachment bolts, loose pins or straps, and broken attachment lugs. Evidence of leakage at the headers will show up as moisture deposits and discoloration of the header metal. Leaks are especially likely at places where tubes are joined to the header. Other likely leakage areas are those with other attachments to the header. Those include vents, drains, and safety valves. You should check the handhole plates for leakage. Corrosion can also be a sign of leakage. However, keep in mind that corrosion is a problem all by itself. Check for corrosion in the same places you check the leaks. Corrosion can be detected by discoloration of the header metal. Cracks in the headers are something else you must watch for. Look for cracks in both the header metal and in the welds in the headers. Check all the welds, both the weld repairs in the header and the construction welds. While you're checking them for cracks, also look for corrosion. Well, that completes our talk on the problems you might run into on the outside of the boiler. The casing is subject to overheating, support failure, corrosion, problems in areas of prior repairs, and problems with construction welds. Also, we've covered the types of problems you're likely to see in casing stiffeners, at casing penetrations, in the boiler drum, and in the safety valves. Remember, each plant is different. Yours may have particular problems that must be checked. Also, always talk to your operators and refer to your plant's instruction and safety manuals. You must clear up any doubts you may have before you start work on a boiler. Well, there are lots of potential problems to watch for while working on or around a boiler, so review all of the material in your text and take care of any questions or problems you might have. Be sure you understand all of the material, because knowing what to look for and where to look for it is what a thorough fireside inspection is all about.